it's, what's his first name? His last name's Dalton, but I don't know. Mr. Dalton, Professor Dalton, got a lot of credit for something about gases that I just think is so funny. Like, no kidding, no duh. In this room right now, it's mostly like 80-20, like 80% nitrogen, 20% oxygen. So you figure the nitrogen and the oxygen combine together to make a collective pressure that's usually like 14 psi or 1 atmosphere or whatever, 760 millimeters of mercury, the pressure together. But we could tease out the pressure of nitrogen, the pressure of oxygen, and that would be their partial pressures. So if they're, now this is really ballpark, and there's more to it than this, I guess. But if it is 80-20, relative number of moles, yeah, this would work. If it is 80-20, relative number of moles of nitrogen and oxygen, then if it's 1 atmosphere, 0.8 atmospheres would be nitrogen, 0.2 atmospheres would be oxygen. It just totally makes sense. So this is an OpenStax figure to kind of show you how this would work. Now there's 3 cylinders, and they all have the same volume. So of course kPa is kilopascals. So the little blue dots is 1 gas. Okay. Then we have the pink dots are another gas. And then we have the yellow dots are a 3rd gas. One of the awesome things about gases versus solids, now liquids diffuse together too, but gases are great if you go ahead and combine them together. Okay, they're going to mix well, and they are, you can kind of see the blue, the purple, and the yellow all in here. And if you were to add up the 300 plus 600 plus 450, you'd get 1350. It's just like, and Dalton came up with that. I'm getting for Dalton. Okay, but we can kind of separate them out or add them together. So these would be the partial pressures, and this would be the total pressure. Works? We're going to kind of take that a step further. We talked about the ideal gas law. PV is equal to nRT. And if we were going to rearrange that solving for pressure, we would say the pressure is equal to nRT over V, right? I'm going to show you kind of a manipulation of this where your volume is going to be held constant and your temperature is going to be held constant. Okay, so again, we could have an assortment of gases. I don't know how my builds go, I can't remember. So we're going to take these 3 gases, gas A, gas B, gas C, and we're going to put them all over here. The volumes are all the same. The temperatures are all the same. Again, I'm going to take these, I'm going to combine them here. And these little things up here, that is my, let's see, there's digital and analog. That would be like my analog indicator of my pressure. So that's whatever my pressure is. So the pressure over here, the subscript T, hope you're okay with this, means total. So total number of moles, and actually sometimes, see if my little thing works, because I'm missing a lot of T's. I'm going to try to put a little subscript T up there where my gases are going to combine. Maybe. Does this work? Yeah, so that's my T, my total pressure. All right. Well, before we combine them, we have number of moles of A and the partial pressure of A, number of moles of B, number of moles of C, partial pressure of A, partial pressure of B, partial pressure of C. Okay, so we have 3 different gases. We're going to combine them over here. And again, this one down here, I would go with a little T subscript, the total pressure. Well, the total number of moles is that the moles of A, moles of gas B, moles of gas C. So this actually, we're kind of getting at, this is a classic sort of problem, but you can actually work this problem if you know, if we do have a common volume and temperature across the board with our individual gases and our combined gases, we can actually work this total pressure by just simply adding the number of moles up and slapping it in there. Not too bad. Alternatively, we can come up with each of the individual partial pressures. Hope you're okay with this. To show partial pressure, you see a little subscript there for what gas it is. So that's the partial pressure of A, partial pressure of B, partial pressure of C. Okay, it's kind of a picture sort of thing. So again, the total pressure when we combine A, B, and C together is equal to the total number of moles times R times T divided by V. Now, I'm going to do like a little math thing. I'm going to basically take this quantity, the sum of N sub A, N sub B, N sub C. Those are moles of gas A, gas B, gas C. And I'm going to substitute it in there for the NT. And it looks like this. I think it's called the distributive property. I'm not sure. But I'm going to miss my little T here. The total pressure. I can go ahead and take each of these quantities that are added together and multiply them by individually by R and T divided by V, and it looks like this. So now I have the total pressure is equal to each of the individual moles times R times T divided by V. Remember, T and V are the same here. So we're coming up to Dalton's law of partial pressures. Each one of these quantities is the partial pressure of the gas for which its number of moles is indicated. Okay. Again, I'm missing a T here. One of these days I just need to go through there because to me that's how I think of it. Total pressure. All right. Blue box. Blue box in here usually means you have arrived at some sort of interesting sort of relationship that you might use down the road. Again, I will put a little T there. The total pressure, it's kind of like I said here a minute ago with the nitrogen and the oxygen. The total pressure that the nitrogen and oxygen exhibits or kicks on us, you can take the partial pressure of nitrogen plus the partial pressure of the oxygen. That's the total pressure. Dalton's law of partial pressures. I did watch, I think it was on a Neil deGrasse Tyson Cosmos series. I think I saw that, but anyway, Professor Dalton was colorblind. If it matters, yes. So again, I would put a little T there, total pressure. It's a new one. All right. So I want to do another manipulation, and we do this a lot in Gen Chem 2. One of the things you guys learned in algebra is if we have an equality like this, we can divide both sides by the same thing, and we're not changing the quantity. So this is what I want to do. Let me put a T there. I basically want to take P sub A over P sub T is equal to this quantity over this quantity. We can do that. It looks like this. It's legit. So now my ratios, make sure we're all on the same page. Here's one ratio is equal to this ratio. Totally legit. The beauty of this is we're going to see, of course, R and T and V, they all cancel. So that ratio actually boils down to this ratio. Sometimes I say it kind of fast, but it's the partial pressure of the component gas A divided by the total partial pressure. That ratio is equal to the relative number of moles of A in the total moles of gas. Well, this right here is actually such an important quantity, we go ahead and it gets its own variable. That ratio, actually, we're going to call mole fraction momentarily. But before I do that, let's rearrange this. If we multiply both sides by the total pressure, we get this right here. Partial pressure of A is equal to the moles of A divided by the total moles times the total pressure. See what? I just think a T is just so important there. So this, we call this, does that make sense, the mole fraction? What is the mole fraction? The relative moles of the component to the total moles. We're talking about things in their gaseous state. So I mentioned, kind of got ahead of myself, we give it its own variable. Its variable is x. So anytime you see x, it'll be the mole fraction of something. And then we'll use a little subscript to say what it is the mole fraction of. And it's the moles of the component divided by the total moles. So now if we go ahead and substitute, instead of that ratio of A, of the moles of A to the total moles, we put that x sub A, it looks like this. Where the partial pressure of any gas, see now this is actually a player, this can take you down the road. Partial pressure of any gas is equal to the mole fraction of that gas, its moles relative to the total moles of gas, times the total pressure of all those gases are exerting. Okay, that's it. Pressure of a gas, the gas mixture is directly proportional to the mole fraction of that gas. Okay, let's work a problem. I can't remember, I think probably I'll draw this one here. And then also kind of let the builds do the heavy lifting. So, you know what it's going to be? It's going to be a box. No curves in this one. And then notice that we have 2.00 grams of carbon dioxide gas. And then we have 2.00 also grams of nitrogen gas. And we've got 2.00 grams of neon gas. And if I had a marker, I could have like different colors, 3 different colors. But there's my gas mixture. It also gives us the volume of our container is 5.00 liters. And then it gives us a temperature, which we're going to have to convert to Kelvin, is 15 degrees Celsius. We can do that. And we're supposed to come up with the partial pressures. So in other words, we want the partial pressure of CO2, the partial pressure of N2, and the partial pressure of neon. There's a few ways to work this, but I'm going to tell you the one that's actually hopefully will make sense to you based on what we just learned, and it will take less time. For each of these, we know that we can come up with the partial pressure of it. I'll just put A generic. If we know its mole fraction times the total pressure, right? I'm going to write PV is equal to nRT because I never know how to rearrange this. If I solve for P is equal to nRT over V. Just now, today, we learned that if you're dealing with a gas mixture, the total pressure is equal to the total moles times R times T divided by the volume, right? So what you're going to see done on the slides here is we are actually going to knock this one out. We're only going to do PV is equal to nRT one time. And then once we have the total pressure, we're going to do this. So it looks kind of like this. That's the strategy. So in order to make this work, I need to come up with the total number of moles. So bada boom, I got to take each of those masses and convert them to moles. So here we go. I don't think I have the molar mass here. See, my bad. Don't do what it's like what your parents say. Don't do what I do, do what I say. So you would want to knock out the molar mass of CO2, which is 44.01 grams per mole. So if I take that 2.00 grams of CO2 times 1 mole of 44.01 grams, and I give myself 3 sig figs, I get 0.0454 moles of CO2. We do a similar thing with, what's the molar mass of N2? 28.02. Yep. So in the second one, I'm going to take 2.00 grams, which was given, times 1 mole over 28.02 grams. That will give me my moles of N2 in 3 sig figs. Looks like 0.0714 moles of N2. And then neon, we just pick it off the periodic table. So I take the mass of neon, 2.00 grams, times 1 mole over 20.18 grams. Again, 3 sig figs, and you're looking at 0.0991 moles of neon. Now we're going to want to hold these handy because honestly, here in a minute, I'm going to sum them up, and that's going to be my N sub T. So I'm ready to kind of plug and chug to knock out my total pressure. But I want to hold these handy because here in a minute, when I do the last part of this, my mole fractions are going to be each of the moles of the component divided by the total moles. So we're going to be revisiting those numbers. So it looks like this. Total number of moles, we add them. And remember, we don't do as much addition or subtraction in chemistry, but it looks like we've got, what, 4 decimals? So we need to allow 4 decimals, and you get 0.2159. 0.2159, yep, moles of total gas. So that's your N sub T. And again, so we're ready to go ahead and come up with the total pressure. Rearrange PV equals nRT. I would suggest when you're working problems, gas law problems, always write PV equals nRT. Don't try to figure it out in your head. Solving for P is equal to nRT over V. So let's kind of recap what we're going to plug in. The total number of moles is 0.2159. And you see where, again, I don't think you can go wrong with putting too much information. I really would put a little T there. Because to me, that reminds me that I've got a gas mixture. We need to fix our temperature. We said we had 15 Celsius plus 273 units. That gives me 288 Kelvin. My volume's good to go, 5.00 liters. It was given in the problem. All right. So, wow, here it is. In the numerator, we have 0.2159 moles. Also in the numerator now is R, 0.082058. Units of R are liters, atmospheres per mole Kelvin. Also in the numerator is our temperature, 288 Kelvin. Notice units of Kelvin cancel. Units of Kelvin cancel, sorry, units of moles cancel also. In the denominator we have volume, 5.00 liters. Now units of liters cancel. Now we just have units of atmospheres in the numerator. Round to 3 sig figs, I get 1.02 atmospheres. Again, I'm going to add a little subscript T here to remind myself what that is. The total pressure. And different problems ask different information. They may ask the total pressure. But now we need to divvy that 1.02 atmospheres up amongst these gases. And we're going to do it this way. So here we go. So what would the mole fraction of the CO2 be? What's in the top? If you look back at your notes. 0.0454 in the top, and what's in the bottom? Yep. 0.2159, exactly. So this right here, this ratio, that is the mole fraction of your CO2. Almost looks like a chi the way I do it. Probably shouldn't do that. I just think chi is pretty, so it should just be an X, mole fraction of CO2. Perfect. Times the total pressure, around to 3 sig figs, so you're looking at 0.214 atmospheres. What's in the numerator of the, when we go to the partial pressure of nitrogen gas? Yep, 0.0714. And then in the denominators, that 0.2159. The total moles, again, times 1.02 atmospheres. Round to 3 sig figs, I get 0.337 atmospheres. Now this is where students would be like, well, Mrs. Snipes, this last one, can't we just get by difference? And you can, but why would you? Getting it by difference, taking the 1.04 minus these quantities should give you that. But let's go ahead and knock it out. So for neon, we would take the number of moles of neon, which was 0.0991, divided by the total number of moles, 0.2159, times the total pressure, 1.02 atmospheres, again 3 sig figs, so you're looking at 0.468 atmospheres. One reason you wouldn't want to go ahead and, like I said, take 1.04 minus these two to get this one is you kind of lose a little bit of information in the limit of your just 2 decimals for that. Okay. Inquiring minds want to know. I'm going to take 0.214 volts, 7 volts, 0.468. I get 1.019. Inquiring minds want to know. All right, let's do another one now. Let's see, how do I say this? All right, I'll say it this way. What is the physical phase of this first reactant, dimethylhydrazine? It is a liquid. How about the physical phase of the N2O4? Also a liquid. How about the physical phase of the N2? Gas. Physical phase of the H2O? Gas, CO2 gas. So, how does it? If you run into a problem where in the problem it's a liquid or a solid, it doesn't add to the gases, okay? It just kind of stays as a blob. So keep that in mind. Hint, hint. Okay, let's see what we got. Since my pen's working, we can write underneath the thing what we got going on. This is balanced. It says we have 3 sig figs, 150 grams of the dimethylhydrazine. So I'll put 150 grams. It works, but it's a little sloppy. Reacts completely with excess N2O4. And it says that all 3 of these gases are going to be collected. Okay, and then the temperature over here is 27 degrees Celsius. So of course we're going to have to add 273 to get it into Kelvin. And it says that they are all going to be bouncing around in the same container with a common volume of 250 decimals. So 3 sig figs, 250 liters. So we have a couple of questions. First off, as their, I don't know, if we call this, take this off, make it easier. If we call the first one A, the second one B, and if you're working problems, you can go ahead and abbreviate, just as long as you say how you're abbreviated, what you're doing. So if I call that A, call this guy B, this guy C, okay, in my volume, it wouldn't be a square. But here we have all 3 of these components bouncing around, okay, A, B, and C, and we're supposed to come up with the total pressure. Well, right off the bat, do you see where we could take, we're not going to do it, but we could. We're going to actually do something a little easier. We could use stoichiometry with that mass, well, not stoichiometry first, sorry, we could take that mass, use the molar mass of dimethylhydrazine and get to moles of this. And then we can use stoichiometry to get moles of N2, moles of H2O, moles of HCO2, get the total moles, and we can plug it into here, right? But there's an easier way. So get the total pressure, and then also get the partial pressure of each component. So we want this, and we want this. Well, we are going to need, let's go ahead and clear. Do we want to hear the secret first? Do you guys remember that, no, that's okay. I'll just let the slides do this, tell the story this time. So let's go ahead and convert that 150 grams of dimethylhydrazine into moles. So here I did do what I'm supposed to do, show you the molar mass of this compound, take 2 times for carbon, 8 times for hydrogen, 2 times for nitrogen, and we get 60.10 grams per mole. If we make our first term 150 grams times 1 mole over 60.10 grams, the molar mass, give ourselves 3 sig figs. So you're looking at 2.50 moles of dimethylhydrazine. Okay, so the catch here, I'm trying to think of how to show this. The catch here is what you told me, that these are all gases, okay? So we know this number of moles, we got it on the previous slide, is going to form 2 plus 4 plus 2. If you add those together, you get 9 moles of gases. You get 9 moles of gases produced for every 1 mole of dimethylhydrazine. So you have just created a wonderful ratio we can use as a conversion factor. The previous slide, we converted 150 grams to what, 0.250 moles of hydrazine. So we're going to use that to our benefit. But again, be careful, make sure you look at the physical phase of everything. All right, so if we use as our first term, 0.250. If we use as a first term 2.50 moles of, I think it's the DMH. Anyway, and feel free to, if you get tired of writing formula, feel free to show it if you want to. And take that times 9 moles of gas over 1 mole of the compound. That's going to give you the total moles of gas produced. So that's NT, that's total moles. 22.5 moles of gas. Now again, make sure you know what you're talking about here. That is my NT, total number of moles. So, this is right. Yeah, I still think that the next thing I do in my slides is I am going to go ahead and substitute in the ideal gas law equation to knock out the total pressure. So the total pressure is equal to the total moles times R times T divided by V. So it looks like this. Total pressure is equal to, oops, sorry, we need to fix our temperature, didn't we? It was given in Celsius, so we take 27 degrees Celsius plus 273. That'll give you 300 Kelvin. It's important that you put that decimal there or it's going to mess you up rounding. Volume was good to go. I guess I didn't write this one. 250 liters, like a lot. Okay. So the total pressure, I'll put a little subscript T there. The total pressure is the total number of moles, 22.5 moles times R, 0.082058. Units of R are liters, atmospheres per mole Kelvin. Also in the numerator, now we have the temperature, 300 with 3 sig figs, 300 Kelvin. In the denominator, we have 250 liters with 3 sig figs, so we have a decimal, trailing decimal after the 0. Round to 3 sig figs, I'll give our units in atmospheres, so we have 2.22 atmospheres. So there were 2 questions here. One was that what's the total pressure of those product gases? That's it. And now we need the partial pressures. So I don't know, now I need a mole fraction, right? And to get the mole fraction, I'm going to go back to the stoichiometry of the balanced equation again. So we said that there's a total of 9 moles of gas produced on the product side. The mole fraction of nitrogen, does this make sense, would be 3/9. 3 moles of N2 over 9 moles total gas produced. What would the partial pressure of, So now we said once you know the mole fraction, you can take it times the total pressure to get the partial pressure. So here we go. Partial pressure of nitrogen is 3/9, or 1/3, right? Times the total pressure, which is 2.22 atmospheres. There is no uncertainty brought by the 3 or the 9, so we're allowed 3 sig figs. That gives us partial pressure of nitrogen is 0.740 atmospheres. So that's the first of 3 gases. We do a similar pattern for the H2O gas and the CO2 gas. So, did it only ask for N2? It asked for all, okay. But we could do if we wanted to. Well, I don't think we'll get through the whole thing, but I do want to go ahead and start a little bit. Now, what's left in the next part is, we've been talking about the ideal gas law equation. Actually, on Wednesday, we need to talk about when gases behave badly, when gases behave non-ideally. But before we go, I need to talk about this. Actually, I'm pretty sure the experiment that you guys are doing Thursday uses this technique. The practical side, or the experimental side, oftentimes we'll create a product gas, but in order to collect that gas, what works well is we're going to, collect it over water. So it looks like this. So of course, here's an Erlenmeyer flask. It's got a stopper. And we have some sort of reaction mixture here, and this is the gases. The gases are allowed to go through this tube, and we collect those gases like this. So what we do, or what we did, is to take this other Erlenmeyer flask, we fill the other Erlenmeyer flask up with water, and then we dump it over into that pan of water. And then we put the little tube like that. So what you're looking at here is the reaction has been going on for a little while. So then what will happen is that the gas that's produced will displace the water. Okay, so over time, this will be getting bigger and bigger as this reaction creates gas. Okay, so because the gas will rise, it's collected here, and that water will go down and down. When it started out, this is total all filled with water. Yep. So the bubbles rush up here and the water flows out. Cool. The problem is, and we address this, is we've been talking about oftentimes gases can be a mixture of things. Just inherent to this sort of setup, you're actually going to have H2O gas up there. It's kind of an extra gas you have to account for. In weather and study meteorology, we talk a lot about water gas, water vapor, And it's kind of strange. You guys already know this, I'm sure, but sometimes the air feels dry, sometimes it feels moist. You have high humidity, that sort of things. There's water vapor in this room right now. Nitrogen, oxygen, water vapor. Okay, so we need to account for the water vapor that's created in this sort of experimental design. So I have some slides that kind of talk about that. A reaction produces a gas that's collected above water, like I just showed you. The trapped gas is a mixture of both the gas that's created by the reaction and the water vapor. I'm actually going to show you, I think this is where I'm going to show you the image again that I just showed you. Does anybody remember that the water was actually in our inverted Erlenmeyer flask? The water was up a little bit from the water in the pan holding it. Okay. If we were to go ahead and, well, maybe it's coming up. This is hard to explain. Looks like this. I'm not going to draw this part, but I'm going to draw this part. So what we saw a minute ago, this was our pan of water. And we had an Erlenmeyer inverted. Oh my goodness. I draw ugly Erlenmeyers anyway. So, okay. And our gas of interest, go ahead and put this as liquid. So this is all liquid. That's just not only liquid, that's water. And this was our tube going up here from our reaction. Okay. So we have gas particles up here. Some of them are the ones that were created by the chemical reaction, and then some of them are water. Water, H2O. I'll just put, I'll put in terms of partial pressure. Partial pressure H2O. What I started to say, and this gets a little tricky, is do you see where I can take this Erlenmeyer and kind of move it up and down? If I were to take this Erlenmeyer in this case and move it down so that now my liquid water in the Erlenmeyer that had the gas was equal to the level of that water, in that case, actually, this total pressure in here would be equal to the pressure of the atmosphere. What I mean by the pressure of the atmosphere, this is what I mean by the pressure of the atmosphere. Okay. Atmospheric pressure. But it only works if you go ahead and get the levels equal. I know, right? Well, put another way, is this right? Oh, I'm going to butcher that. Oh, okay. So gas collecting container is filled with water, just like I kind of described. Before we invert it, I told you we filled it with water, put your hand over it, and go ahead and set it in the container, this thing. Go ahead and start our reaction, and then the gas flows up here and it displaces water. That's it. This is what I tried to explain just now. If the liquid level outside and inside the container are the same, the gas pressure inside and outside are also the same. In other words, the total pressure of these gases is equal to the pressure of the atmosphere. I'm trying to think, if it's too high, that means it's, I think I have a slide here to say it so I don't butcher it. This, as you might imagine, it's not going to work if what you're producing is reactive with water. Bad. But a lot of times the gases that you're creating are not going to react with water, so they actually will displace the water quite well. This was why I reintroduced this. In this case, the total pressure in here would be less. Does that seem right to you? Total pressure in here, that scenario, total pressure within the flask is actually less than the pressure of the atmosphere. If I were to go ahead and make it so the water level was below, water level inside the inverted Erlenmeyer was below that water, then it would be greater than. Then my total pressure within my flask would be actually greater than. It's just a visual thing, that's what I call that too. If they're equal, So, based upon what we've just been talking about, we need to tease out the effect of the water vapor. You can't blow it off. I wish you could, but you cannot. So, for instance, in this case, if I had two product gases, I could go ahead and say my total pressure is equal to the partial pressure of my H2O, just inherent to the experimental design, plus the partial pressure of A plus the partial pressure of B. Just got it. So in order to actually have this all make sense to you, I need to talk a little bit about equilibrium vapor pressures. So, equilibrium vapor pressures. Well, first off, we have, if we're just, and I want to talk about equilibrium vapor pressures of water. Let's try to do it this way. Have you ever seen, or can you picture a terrarium? Okay, where you have a closed system, you add water in there, and it kind of creates its own little water cycle. Because in a terrarium that I'm thinking of anyway, basically you have water that will evaporate from the soil or whatever in your closed little system, and it will condense on the sides, okay, then we'll right back down. You've probably heard of the word saturated. Basically what you have in your little terrarium is you have a saturated situation. You have all the water vapor that can be held in that volume at that temperature, okay? So the way this works, or what you're looking at, actually is an equilibrium vapor pressure curve. We're talking more about these in general chemistry too. We'll talk more about gases in Gen Chem too. So what you're seeing is, have you ever heard that cold air holds less water, warm air holds more water? Have you ever heard of that? I don't know, we talked about it in meteorology a little bit. And it's true. Cold air, okay, it holds less water. Okay, warm air holds more water. This curve actually is what at this temperature the equilibrium vapor pressure will be. So there are some crazy temperatures on there, but if we just kind of pick out, let's see, room temperature, what are you talking, 25 Celsius or so? Let's see, 20, 30, so right here. So we're kind of low on the curve. Go over here, okay? And that right there at saturation is what the equilibrium vapor pressure of water is. Notice if you're dealing with, you increase the temperature to 80 Celsius, ooh, that's terrible. Okay, this actually then is what the equilibrium vapor pressure of water is, etc. Equilibrium vapor pressure. Equilibrium vapor pressure. Well, vapor pressure, okay. The equilibrium part. Equilibrium means that something, the way I think of it, when I think of equilibrium chemistry, I think of kind of this. Equilibrium, going back and forth. In the case of water, what are we going back and forth between? That. It's a dynamic equilibrium. It's right at the edge. It creates a saturated situation. Okay, and actually I have some videos to kind of show you, reinforce that. And this is one thing I don't like about chemistry, and actually meteorology does this too, less, I think. But anytime you see vapor pressure, that is the equilibrium vapor pressure. I'm not real thrilled about it. Okay, I like this. Check this out. So I have, this is like a dome or bell-shaped bell jar, okay? So this is our system I was talking about. This is the terrarium. This is totally the terrarium, okay? Now, does this look like evaporation to you? Hopefully it does. Because here we have these cute little water molecules. They're going from a liquid to their gaseous state. This is the beginning of your terrarium. We let a little bit of time lapse, okay? Now notice that if we were to count the red up ones, that's evaporation. What are the blue ones? Condensation, yep. Who's winning out, evaporation or condensation? Evaporation, yep. So one way to think of it, and again, we'll kind of hit this in Chem 2, is, let's see, that is evaporation, right? Bless you. Bless you. And this is condensation. Evap, condense. Does that look like that kind of thing? Well, you know what's going to happen. Who's winning out here? I don't think anybody's winning out. So in here, we actually have the rate or the amount of evaporation is equal to the rate or the amount of condensation. So that is at equilibrium. It's a beautiful thing. It's just so lovely. What would you say about the particles in jar B versus jar C? C finally has more particles, right? So honestly, if I could put a little partial or a little pressure gauge there that was particular only to water vapor, that would be the partial pressure of water vapor. And again, that kind of goes, it's temperature dependent. So as I jack up the temperature, picture taking C and putting a flame under this, what's going to happen to the partial pressure of my water vapor? It's going to go up. It actually goes up for two reasons. One is because there's more water vapor, and the other is they have more kinetic energy because you just heated them up. It's so cool, so cool. All right, these are short videos. I had to turn down the volume again. Well, why don't we just, I will start with these videos on Wednesday. So hopefully Gavin's here. But, so I did post these. I posted some of them, not the ones, the collecting a gas over water.